Hi guys, today in this video we're going to go over the next two sections of our notes for Unit 6. We went over 6.1 through 6.3. As a review in class, today we are going to do 6.4 and 6.5. We're going to be talking about heat capacity and calorimetry. Previous year chemistry class, Q equals MC delta T, and then we're going to be looking at those phase change diagrams. Again, I think something that you guys have seen in previous classes, but we're going to be reviewing those things and all of the calculations that go with it today. Before we get into all of the calculations, let's talk about, again, just the definition of heat capacity or specific heat. Really, those two things are going to mean the same thing as we refer to them in the different equations that we're going to talk about. What you guys need to know is that specific heat is the amount of energy needed to increase the temperature of something. That's really the main idea. There are some specifics to it. How much energy does it take to raise the temperature of 1 gram of a substance and raise it 1 degree Celsius? But basically, we're looking at how much energy does it take to raise the temperature of something. And so when we're dealing with substances that have higher specific heats, they have more energy is required to change the temperature. Water has a really high specific heat value. We're going to see that it has a specific heat of 4.18 joules per gram degrees Celsius. And you guys will see that those units match really the definition. How many joules of energy does it take to raise the temperature of 1 gram 1 degree Celsius? So for water, it takes 4.18 joules of energy if you have 1 gram of water to increase the temperature 1 degree Celsius. So if we're comparing two different substances and we're looking at two substances that have different specific heat values, the one with the lower specific heat, if you add the same amount of energy, so let's say that you've got 1 gram of water and the specific heat is 4.18 versus 1 gram of aluminum, and aluminum has a specific heat of 0.39, it only takes 0.39 joules to raise the temperature of 1 gram of aluminum 1 degree Celsius. It takes 4.18 joules to raise the temperature of water. If I add 50 joules of energy to each one of those things, aluminum is going to have a greater change in temperature because it doesn't require as much energy to change the temperature in the first place. So if I add 50 joules, the temperature is going to go up more. The substance with the lower specific heat value will have a greater increase in temperature. The water will not increase its temperature as much. So we do have to make sure that we are paying attention to units. Specific heat units are usually given in joules per gram degrees Celsius. Every once in a while, though, they'll give you or ask you about something called molar heat capacity. It's the same idea. Instead of how many joules of energy does it take to raise 1 gram 1 degree Celsius, it's just how many joules of energy does it take to raise 1 mole of a substance 1 degree Celsius. So the conversion is just a regular conversion, basically, of grams to moles. And so here's how you would set that up in order to figure out molar heat capacity. If I have 4.18 joules over grams degrees Celsius, I want it to be joules over moles degrees Celsius. So the units I want to convert are going to be from grams to moles. And since we're dealing with water, water's H2O. I know that oxygen is 16. Each hydrogen is 1.01, so that's going to give me 18.02 grams per 1 mole of water. All that's going to do here is it's going to cancel out my units of grams, and it's going to give me 75.3, we'll multiply across, joules per mole degrees Celsius. So it'll take 75.3 joules of energy to raise the temperature of water by 1 degree Celsius if you have 1 mole of water. So that's just a quick conversion from specific to molar heat capacity. All right, let's review this equation really quickly. We're going to be using it in lots of different ways throughout this whole unit. Q equals mc delta T. So let's remember what everything stands for. So Q is our heat energy, and that's always going to be in joules. M is going to be our mass. And in chemistry, we're dealing with small amounts of substances. So that's going to be in grams. When you get into physics and you use this equation, sometimes they'll deal with kilograms here, but we're going to be dealing with our mass in grams. C is our specific heat value. Okay, so specific heat, sometimes they call it specific heat capacity. Same thing, that's joules per gram degree Celsius. Just talked about that one. And delta T, super important. We've seen delta in some other equations, always means change in temperature. And it is important the order in which you put those things. It's always going to be final temperature minus initial temperature. And the reason why that's important is because we want to know if energy is being released or absorbed. So you can have positive Q and you can have negative Q. If you have negative Q, then that just means that it's losing energy. Positive Q would be absorbing energy. So we'll go ahead and write that down. Energy absorbed for positive Q, energy lost for negative Q. That's going to be important for some of our calorimetry questions. Calorimetry is just measuring heat transfer between objects as one thing cools down and the other one heats up. So sometimes you guys will be using Q equals mc delta T just to calculate how much heat is absorbed or released by one particular substance. In this next section, we're going to look at what do we do when we combine two things together and something is at a higher temperature and it is combined with something at a lower temperature. So in this example, we've got a 15-gram piece of aluminum metal, and it gives us the specific heat of aluminum is heated to 100 degrees Celsius, and it's placed in 300 milliliters of water at 27 degrees Celsius. Okay, so here's what's happening. We have to kind of visualize what's going on here. I've got aluminum, and aluminum is going to be at 100 degrees Celsius. And I'm going to take that hot piece of aluminum and I'm going to put it in water. That water is at 27 degrees Celsius. So what I need to realize is going to happen is when I put those things together, the aluminum is going to cool down, the water is going to heat up, and they're both going to reach the same final temperature. That's going to be their equilibrium temperature. They're going to be reaching what is called thermal equilibrium, the same temperature after the aluminum has lost energy and after the water has gained the energy. So the amount of energy that's lost by one thing is going to be the same as the amount of energy that's gained by the object that it is combined with at the lower temperature. So in this case, the aluminum is going to be losing energy. So we're going to go ahead and make that negative because it's going to be decreasing in temperature. Whichever substance starts out at the higher temperature is the one that's going to lose energy, is the one that has to have the negative next to it. That's going to equal the positive amount of energy that the water is going to absorb. So now I can go ahead and I can plug in my equation for Q, which I know is Q equals mc delta T. So I'm going to leave my negative stuff over here, mc delta T. And this is where I'm going to plug in, sorry, that's a T. That's where I'm going to plug in everything for aluminum. And over on the positive side, I'm going to plug in positive mc delta T. This is where I'm going to plug in everything for water. And I'm going to set those two things equal to each other. I'm looking for what is the final temperature of the water, but what we need to realize is that the final temperature of the water and the final temperature of the aluminum, are the same. So when I expand out this equation, let's go ahead and plug in some numbers here. So let's plug in my mass of my aluminum is 15 grams. The specific heat of my aluminum is 0.89. And TF, I don't know. Remember, delta T is always final minus initial temperature. TF, I don't know. I'm going to try and find that. The initial temperature of my aluminum is right up here, is 100 degrees Celsius. So I'm going to go ahead and plug that in there. Over on the other side, I'm going to plug in everything for my water. The mass of water, 300 milliliters means 300 grams because the density of water is 1. That's really common for them to not specifically give you the mass in grams of water, but they expect you to know the density of water is 1, so however many milliliters you have, that's how many grams you have. Specific heat of water is 4.18. And then we don't know the final temperature of the water. That's what we're looking for. But the initial temperature of the water is 27. Okay, now we're going to go ahead and we have some distribution things that we need to do. Let's go ahead and multiply these numbers together first. 15 times 0.89, that's negative. That's going to give me negative 13.35. And then we'll leave TF minus 100 in parentheses for now. We'll deal with that in a second. Just kind of clean up everything as much as you can to make the math as easy as possible, because we are going to have to combine like terms on the same side of the equation. So now I'll do 300 times 4.18. That's 1,254. And we'll go ahead and leave TF minus 27 in parentheses. All right, now I'm going to need to distribute through my parentheses here so that I can combine my TFs together on one side. So let's go ahead and do that. So I'm going to get negative 13.35 TF, and then negative times negative is going to give me plus 1335. That equals 1254 TF. And then minus 33,858. That's what I get when I multiply 1254 times negative 27. All right, combining like terms, I need to get all of my TFs together on one side. If I can make them positive numbers instead of negative numbers, that's the easiest way to do it. So I am going to put my TF terms over on the right side of the equation. So 1254 plus 13.35, I'm going to get 1267 TF on the right side. Then I'm going to add 33,858 to the other side. It's going to give me 35,193. And then I'm going to go ahead and solve for TF. TF should give me 27.8 degrees Celsius. Started at 27 degrees Celsius, ended at 27.8 degrees Celsius. The water, right? The water went from 27 to 27.8, only an increase of 0.8. The aluminum went from 100 all the way down to 27.8. So this final temperature right here is 27.8 degrees. So just like how we talked about, water has a high specific heat value, so the temperature doesn't change very much. Aluminum has a very low specific heat value, so the temperature can change quite a bit. Okay, why don't you go ahead and take a minute to work through this practice problem. So we've got a metal pellet having a mass of 22.34 grams at 90 degrees Celsius, placed in a calorimeter. A calorimeter is just a container that doesn't allow heat to escape. Contains 50 milliliters of water. The water temperature rose from 21.0 degrees Celsius to 23.17. Important thing to notice here is that if this is the final temperature of the water, remember that that is also the final temperature of the metal. So you do know that this time. In the previous question, we were trying to find the final temperature. In this one, we already know it, but we are trying to find the specific heat of the metal. So we've got two things. We've got the metal that is losing energy. We've got the water that is gaining energy. Go ahead and go through the same process that we did on the previous question and pause the video for a second. Actually, I think I'll pause it and have you guys enter your answer after you solve the problem. So go ahead and work through this in your notes until you get an answer that you can enter. All right, you should get a specific heat value of 0.30 joules per gram degree Celsius for the metal. We're going to take a look at heating curves real quickly, and then some calculations involved with those. you need to know a couple of definitions first. A lot of them are definitions of things that you already know: boiling point, melting point, all of that kind of stuff. But vaporization and evaporation, those are important to know the difference between those. First of all, they are both substances going from liquid to gas. Vaporization is actually what it's called when it happens when you heat up something to its boiling point and it turns from a liquid to a gas. When you boil water, that is actually vaporization. If something evaporates, that can happen below the boiling point just because of the breaking of intermolecular forces, not necessarily because you heated it up to its boiling point temperature, but because those intermolecular forces are broken. Both of those are going from liquid to gas. Let's see. So heat of vaporization is how much heat is needed to vaporize a liquid, turn it from a liquid to a gas at the boiling point. Condensation is the opposite of vaporization. We've got gas going to liquid. And so we're going to be calculating how much energy does it take to do that? How much energy does it take to evaporate or vaporize, I should say, vaporize a certain amount of liquid? How much energy is released if that same gas condenses back into a liquid? If something is really volatile, it means that it evaporates very quickly. So this is what a heating curve diagram looks like. For any substance, you'll see the areas where you have increasing temperature, and you'll see these flat line portions of the graph. We're going to take a look at this graph specific to water as far as temperatures go. But if it's something else besides water, it'll look exactly the same, but the flat line sections will be at different temperatures. And so what a heating curve represents is all of the different states of matter. So from section A to B, this would represent when water is in the solid state. C to D would represent when water is in the liquid state. And E to F would represent when it's in the gaseous state. When we have these flatline sections, really important with these flatline sections to understand that these represent our phase changes. So if you want to like highlight those, if we are going from left to right, then this is going to be going from solid to liquid. This is going to represent melting as we go from left to right. Going from liquid to gas is going to represent vaporization. And then if we're going from right to left, then I'm going to have the opposite of those things. So I'm going to have condensation as I go from right to left, and then going from liquid to solid, I'm going to have freezing. So melting point, freezing point temperatures are the same. The boiling point temperature, the temperature at condensation, those are the same temperatures. If we're talking about water, this happens at 0 degrees Celsius. This one happens at 100 degrees Celsius. They expect you to know those temperatures for water. 0 degrees is when ice starts to melt. 100 degrees is when water starts to evaporate. So also important to know is when you can use certain equations here. So every time you have temperature increasing, that is section AB, that is section CD, so A to B, C to D, and E to F. Anytime you have that section and you're calculating how much heat is absorbed during that section, you can use Q equals MC delta T because you have a change in temperature. But these other sections, these flatline sections, I'll write it in green down here, you cannot use Q equals MC delta T here or here because the temperature is not changing. But there is energy that is still being absorbed or released, depending on which phase change you're going through. The energy that's absorbed is being used to break apart the intermolecular forces. You're not breaking apart bonds here, right? Like if I'm going here, I'm going from H2O as a liquid to H2O as a gas. Still H2O, right? I'm not breaking apart hydrogen and oxygen bonds. I'm breaking apart hydrogen and oxygen molecules. And so that does take energy. So energy is still absorbed here. It's just not being used to increase the temperature. It's being used to turn it from a liquid to a gas, and then down here in BC, from a solid to a liquid. So there are different equations that you're going to use here. Let's talk about let's talk about section BC first of all. You're going to use Q equals the mass times the heat of fusion, or the number of moles times the heat of fusion. This right here is where we're going to be using our heat of fusion to do our heat calculations. Up here, we're going to be using heat of vaporization. And what you multiply it by completely depends on what units they give you. If they give you heat of fusion in joules per gram, then you'll multiply it by mass. If they give you joules per mole, then you have to multiply it by moles. For section D, E, you're going to do the same thing. It's just going to be heat of vaporization instead. And again, it depends on what units they give you the heat of vaporization. And do they give it to you in joules per gram? If so, multiply it by the mass. If they give it to you in joules per mole, then multiply it by the number of moles. So there are some numbers that we need to know. For water, I'll put them right here, I guess. You'll need to have them in your notes when we do our calculations in class. So having them in your notes is going to be helpful. Okay, so let's talk about the heat of vaporization. This is all for water, okay? If it's not water and it's something else, then they'll give you the numbers. They'll give you the water numbers too, but on some of the calculations we're going to do in class, I don't have it on there. So I want you guys to have it in your notes. Heat of vaporization for water is 40.79. That's kilojoules per mole. Let me give you grams too. So 2,330 joules per gram. So you'll see either one of those. Heat of fusion of water is, for whatever reason, well, just because a mole is more than grams, I guess, they give it to you in kilojoules per mole. So 6.01 kilojoules per mole. And then that is 335 joules per gram. Okay, so notice heat of vaporization is a much bigger number than heat of fusion. It takes a lot more energy to break apart liquid molecules and turn them into a gas than it does to turn solid molecules into liquid molecules. Okay, the other thing you guys need to know is that the specific heat of water is different depending on the state of matter. So let's write that down too. So the specific heat of ice, the specific heat of water, and the specific heat of water vapor, which is steam, are all different. So when you're using Q equals MC delta T, you're going to use different specific heat values depending on which section of the graph it is. Is it in the solid section, the liquid section, or the gas section? So for solid water or ice, it's going to be 2.1 joules per gram degrees Celsius. Liquid water, we already talked about, is 4.18. And then steam, water vapor, is 2.0. These are all in joules per gram degrees Celsius. All right, let's do one example of a heating curve calculation, and then that will be the last section of the notes that you guys will need before we come to class, and we'll do a bunch of heat calculation practice. Okay, so I'm going to change this question just a little bit. Let's go ahead and change it. Example, how much energy is needed to convert 200 grams of ice at negative 50 degrees Celsius to water? Let's make this, it says water, so let's change this to 75 degrees Celsius. Okay, if I think about my heating curve, and this is the general shape of my heating curve, it's starting with ice at negative 50 degrees Celsius. So things I need to know. Remember, I need to know that first line is at 0 degrees Celsius. I need to know that this second line is at 100 degrees Celsius. So I'm going from negative 50, which is down here somewhere, negative 50, and I'm going to go all the way up to 75 degrees Celsius. I want to know how much energy it takes to get from negative 50 all the way up to 75. So what you cannot do is you cannot just do Q equals MC delta T and plug in your change of temperature from -50 to 75 because there are different specific heat values. There's this flat line section that we have to calculate. So I'm actually going to number these sections 1, 2, and 3, and I actually have to do 3 different calculations and then add them together. So for section number 1, I can do Q equals mc delta T because the temperature is changing. The mass is 200. The specific heat, now on the previous slide, I talked about the specific heat of ice being 2.1. So we're going to go ahead and plug that in. Now, the other thing is my change in temperature. Final temperature, I'm talking about just the change in temperature right here in this section. So my final temperature in that section is 0. My initial temperature in that section is -50. So that's going to give me 21,000 joules. And I'm going to go ahead and convert that to kilojoules because I will probably need that later. So that's section 1. Now I'm going to go ahead and calculate section number 2 separately. And section number 2 does not have a change in temperature. I cannot use Q equals mc delta T. I have to use Q equals, let's do it in moles. Oh, you know what? I could do it either way, actually. They gave me grams, and I gave you the specific heat value in grams. So let's go ahead and do that. So 200 grams, and then my heat of, I need to use heat of fusion when I'm at that melting point temperature of 0 degrees. Heat of fusion, I gave you 335 joules per gram. Okay, let's go ahead and I'm going to need my calculator to do that. I haven't done that part yet. Go ahead and calculate that number of joules, and then also go ahead and convert that into kilojoules. And then for section number 3, we're going to go ahead and do the same thing. Section number 3, I have a change in temperature, so I can use Q equals mc delta T. My mass is 200. My specific heat value, this is of liquid water, is 4.18. And my change in temperature, my final temperature, I'm talking about change in temperature just for this section, is 75. My initial temperature in that section is 0. So that's going to give me 83,600 joules. That's 83.6 kilojoules. Okay, I went and I got my calculator. So let me go ahead and calculate that heat for section 2. So we have 67,000 joules, which is 67 kilojoules. So now, if I want to figure out the total heat needed to change ice from -50 degrees Celsius to water at 75 degrees Celsius, I need to add all 3 numbers together. So I'll add 21 kilojoules plus 67 kilojoules plus 83.6 kilojoules. And that gives me 171.6 kilojoules of energy. Okay, so with our heating curve, you have to figure out what parts of the heating curve are involved in the calculation, separate it into the different sections, calculate them separately, and then add them together. So we're going to do a lot of practice with this in class, with calculations with heating curves and our calorimetry calculations. So I will see you guys in class, and we will practice it in class, okay? So I will see you guys then. Have a good day.